Growth calculations. 5 equations enable us to understand, measure, and calculate population growth and diversity. We're going to define rate and population growth. There are 2 types of population growth, exponential and logistic, and we're going to measure diversity using Simpson's diversity index. These are the equations that are provided for your use on the AP Biology College Board examination. We are going to be solving problems using all of them. Rate of population growth, or dN over dt, is the birth rate minus the death rate of organisms per time. For solving problems, it is often expressed as the rate per capita, where the rates are divided by the total number of organisms in the population, n. For example, if a population of 3,000 mice experienced 2,000 births and 1,500 deaths in a year, the population growth rate can be expressed in 2 ways. We can have dN over dt equals b minus d, where that's 2,000 mice born minus 1,500 mice dying, giving us 500 mice per year increase. We can also divide it by n, and then we have population growth per capita, or per mouse. So we would have that same math, 2,000 minus 1,500, but then we would divide it by 3,000, the initial population of mice. And that would give us 0.16 mice per year increase per capita. Birth and death rates can also be expressed in 2 ways. We can have it in mice per year. So like, for example, B equals 2,000 mice per year means that 2,000 mice were born that year. 1,500 mice die per year. So therefore that would be positive 500 mice per year. You can also express this per capita. So divided by n, the total number of mice in the total population. So 2,000 mice per year for 3,000 mice gives you plus 0.67 mice per year per capita. So that's a gain of 0.67 mice per mouse. And then here we have 0.5 deaths per year per capita. Example 1, population growth. A population of 153 owls are introduced to 100-acre woods. The population's birth rate is 0.692 per year per capita, and the death rate is 0.146 per year per capita. What is the rate of population growth per capita, and is it increasing or decreasing? All right, so since both of these are per capita, and we're asked for the rate of population growth per capita, we don't have to do any converting. We can just use this equation. B minus D gives us the population growth rate, 0.546. And since this is a positive number, that means the rate of population growth is increasing. Species that are growing exponentially are said to be in an ideal environment. There are plenty of resources and space, with no disease or predation. Population growth is unrestricted. It is usually impossible to monitor every individual in a population. Instead, multiply the maximum per capita growth rate, Rmax, by the population size. Exponential growth here is plotted, and it looks like a J-shaped curve. An example is the initial growth of bacteria in a culture where there are almost unlimited resources for the initial population. Example 2, exponential growth. There are 40 ogres in Shrek's swamp. The population is under carrying capacity, also known as growing exponentially. If Rmax equals 0.043 per year per capita, predict the population size for the next year. All right, so we have our equation here. dN over dt equals Rmax n. We're just going to plug in our Rmax value, and we're going to multiply it by the initial population, 40, and we get 1.72, which means the ogre population is increasing by 1.72 ogres this year. Now you cannot have 0.72 of an ogre, so it's going to be either 41 or 42 ogres. Example 3, population growth. A population of 2,682 American goldfinches are introduced to an area of Ramapo State Forest. Over the next year, the goldfinches show a death rate of 0.427 per year per capita, while the population drops to 2,247. What is the birth rate for this population? Is this proving to be a suitable habitat? Alright, so our first step is to calculate the population change. So you can see that we've lost 435 finches. Then, what's the population change per capita? So we're going to divide that change by the initial number of goldfinches, 2,682. And we get that that is a negative 0.162. So it's negative population change per capita. Finally, we calculate the birth rate per capita. So we have our equation here, and we solve it algebraically for B for birth rate. So we're going to add D to both sides. And then we already calculated this on the previous slide. It was negative 0.162. And we know the death rate was 0.427. It was given to us in the problem. Therefore, the birth rate was 0.265. This is not a suitable habitat since the birth rate is less than the death rate. Logistic growth occurs when the population is restricted in size due to limited resources. The maximum number of the individuals of a species that the habitat can support is known as the carrying capacity. Most species grow exponentially until they reach their carrying capacity. Then they fluctuate up or down as the resource availability changes. When population is plotted against time, the graph is usually shaped like an S. Mathematically, the curve starts as an exponential plot and finishes as a constant line. This could represent a bacteria population that has more resources than it needs in the beginning. But as the bacteria population grows exponentially, they begin competing for the original resources, and the population would stop growing when it reaches its carrying capacity. Example 4, logistic growth. The New Jersey state flower, the common blue violet, has a population of 60 in a field. It cannot continue to grow exponentially due to lack of space. The carrying capacity for their patch is 140 blue violets. Their growth rate is 0.3 per month per capita. What is their population growth rate at the end of a month? Round to the nearest tenth. Okay, so we have our equation here for logistic growth. We're given some values. We're given the growth rate is 0.3 per month per capita. We have a starting population of 60, so that's going to be N. And the carrying capacity is K, that's 140. So when we plug all our numbers into our equation, we get 10.3. The population growth at the end of 1 month is 10.3 blue violets. Simpson's Diversity Index measures the diversity of a community. It considers the number of species present, as well as the abundance of each species. The resulting value is between 0 and 1, with 0 representing no diversity, where all individuals in an area are members of the same species, and 1 representing maximum diversity. Example 5, Simpson's Diversity Index. Consider the below table. Calculate the Simpson's Diversity Index of this grouping of organisms. So we have A through H, this many different species, and these are how many of each species we have. First, we need to calculate N, the total number of organisms. So we're going to add up all of these numbers. When we do that, we get 17. Now we can use our equation. 1 minus, now we have a summation. So for each species, we're going to insert lowercase n, which is the number of that species. So for example, species A, we have 4 of them. So 4 is going to go in the top. And 17, the total number of organisms, goes in the denominator. We're going to square that term, and then we're going to do that again and again for each type of species. At the very end, we get a number, 0.846.